Good afternoon. My name is Michael Jassowski, and I'm joined here with Todd Oas, who is going to help answer questions at the end when we get there. I've been working at Intel for 27 years now. When I first started, I was a design engineer on the 486 project. Anybody here ever used a 486? All right, a couple. I was concerned that nobody would even know what that was. Back then, the microprocessors had like 1.2 million transistors on it. Today, it's tens of billions. So the scale has changed, just like the scale is changing in data. So just a little bit about Intel. Of course, if you crack open your laptop or server or go to your cloud provider and peek into their data center, good possibility you're going to find Intel microprocessors inside. But we also do a bunch of other stuff. And so I've got this marketing foil here that goes into some of that. I want to talk about some of the numbers, not all the numbers on this slide, but the third and fourth numbers on the top row are pretty important for this presentation. One is the number of users at Intel. This is a number from 2018. It's about the same today, somewhere north of 100,000 users, or 100,000 employees, excuse me. And our R&D budget is about $13 billion in 2017, probably a little bit higher than that now, but on that order of magnitude. And why that number is important is because I'm part of the group that spends that money. So our group is responsible for figuring out the optimal way of spending some of that money. And the money that we spend is basically focused on the R&D engineering team. So we buy whatever they need to get their job done. From the software that they use to design these big monster chips, which can be very expensive software. Just as an example, a single seat of one of the licenses used to design the software could be north of $1 million just for a single seat for list price. So those are the EDA tools, electronic design automation tools that we use. We also outfit all the labs, oscilloscopes, testers, things like that. We buy all that equipment. We buy IP, which are little pieces of the design we get from other companies that we stick on our products. And then also we work with the teams to get outsource resources to help do the design. So I'm going to focus on one aspect here that's highly data intensive, and that's the electronic design automation software environment. We track every single use of all the licenses worldwide across Intel. And we have billions of license checkouts per year, billions of license hours of use of that software a year. We have tens of thousands of engineering users accessing those licenses 24/7 across the world. There's thousands of different features that get used. You know, each application might have a dozen or so different features that needs to be tracked. Those are installed on hundreds of licenses servers running hundreds of licensed daemons, all collecting that information, and that gets rolled up by our group. And we do it with a very few people. We got 5 operations people and then 5 analytics team resources who are mostly in the room today. So a bit about what we use that data for. Like I said, we're trying to optimize cost. There's hundreds of different users worldwide that access this data. And there are a variety of different types of people. So we've got a couple of power users that we give Explore access to because they understand the underlying data model and we can trust them to do sane things with the data. But a majority of the users are very infrequent users. So these are people like finance, like operations, like engineering teams that need to use the data maybe during a planning operation, which might get redone once a quarter. So they don't have a lot of time to learn a lot of details about the tool. We like to provide them with dashboard access only. just to give them a curated environment that they won't hurt themselves with. But with all those different users from a variety of different business groups, it'd be difficult to come up with all the dashboards that they need to get their job done. And even if we could design hundreds of different dashboards for all the purposes that they need, then finding the dashboard that they need to answer the question they have becomes extremely difficult. The last part of our problem is we've got a very complex data model. We've got and a lot of that data has high cardinality. So let's talk a little bit about high cardinality data. What is it? So basically, it's any data that's got a bunch of different distinct values. Example, usernames in a company that has more than a dozen users, cities in the U.S., countries in the world, zip codes, anything that's got more than a dozen values. If you use that data in a pivot table or a stack column chart, you're going to have a problem because you're only going to be able to see a subset of the data. By default, you get 50 columns with Looker. You can increase that somewhat, but you're going to have an impact to your browser performance even if you do that. So what we really want to be able to see is, even though we have thousands of categories, we'd like to see the top end, where you could select maybe 20 or 30 different things. So before I go into the description of how we're doing this, let's talk about the problem with high cardinality. So we start off here with $35 million dollars of revenue, and we drill into it. Eventually, we get to a point where we're trying to show too many things on the chart, and only returns the top 50 of them. And instead of having $35 million of revenue, we're only showing the top 4 million. We don't know how much the rest is because we've lost that information because we're only showing the top 50. And there's no way to sort the data to get the top values. You're picking the top 50. Once we get it into Looker, it's going to sort those dimensions alphabetically. So we're not going to get, by default, the top highest values. And the other thing we'd like to be able to do is get that top end value all based on the filter settings that we have already in our dashboard. So we need to have a top end visualization that allows an analyst to go through and dig into the data and figure out what's driving some of the data patterns that they're seeing. Let me start off with a demo that shows you how this is eventually supposed to work. So here we got the $35 million of revenue. We're going to drill into it by borough. There's a few boroughs, so we still see all the data. And we're going to drill into it by zone. And there's lots of different zones. So now you can see we've got the other category on top. So it still gives us a good idea what our total data set is. Then we drill into that further by payment type, and we can see a breakdown of cash versus credit. And then you can drill into another value here, which is by day. Now we're breaking that week data into a day. We can drill into that day by hour, and we can see how that's spread out over the hour. And then we can even go into the dashboard filters and change how the stacking is being done, so we can see it stacked by payment type. So it's flexible. Basically, we're rearranging the X and Y categories on this chart on the fly without having to go into the Explorer environment. All right, so how do we do this? So what we do is we create a new super view for all the top-end functionality that we're going to be adding here. It's going to extend the primary view. So we're going to use a lot of the tricks that maybe you've picked up in some of these hands-on labs. So we use extends a lot. We're going to use a lot of liquid parameterization to implement some of this functionality. And we're going to join that top-end view and a rank view into a new top-end Explorer. And then we're going to use the rank category as the tart's pivot dimension. And then to get some of that time-based drilling in large data sets, we have pre-aggregated materializations, or PDTs, that will use what we call liquid table steering to go get the right data. So let's dive in on how we're going to do that. So the top-end super view. This is going to extend our initial view, which was yellow trip data. We're looking at yellow cab data here. And we're going to add a couple of parameters, a couple dimensions, and a filter. So let's look at that first parameter. The first parameter is our stack by parameter. This parameter is going to be a filter that is going to be able to set what the dimension is that we're going to be stacking. And so we're going to have a bunch of suggestions. Each of these suggestions is a dimension, either in the base view or in any of the views that gets joined in with that base view if you have a complex model. Then we're going to add a parameter called, or a dimension called stack dimension. Now this is hidden. It's basically what's going to be used to join into the ranking view. We use a little trick here. We have at the bottom there, the SQL statement has a lot of different dimensions referenced in it. If we use the $brace syntax that Looker provides, it's going to automatically create joins in our model and put way too many joins in. We're only joining in one thing that's being stacked. So if we create all those joins, it's going to be a performance hit. So what we do is we sort of put the naked field names in there without the $brace syntax, and then that doesn't cause the superfluous joins. And then the HTML statement above basically is a no-op statement, but it references a value that's within that dimension, a throwaway value that's in that dimension. Let me show you what that looks like. So at the bottom there, we have a view that got joined into our yellow trip data view. And we create a measure called top-end join trigger, which basically just returns a SQL1, which is a no-op. Doesn't do anything to your SQL. We hide it. And whenever that dimension gets selected in the filter set, that will trigger the join to happen. So we work around the superfluous join that way. We've also added a stack limit filter, just basically a number that allows you to tell how many things you want stacked up in your final visualization. And then, okay, so we get to create a ranking view. So this is the view that basically generates what rank each dimension should show up in the chart. It's going to figure out the top end things. So it's got a drive table. Now the drive table, basically it's a native drive table based on the top end super view. And it's going to calculate a rank number based on all the filters that are set. And we're using the bind all filters, yes. That's a new parameter in version 6.20. It used to be we'd have to enumerate every single bind filter that's going to show up on our dashboard, which was kind of tedious. So this is a nice, helpful time savings measure. And then we create a dimension in that rank view called the unranked dimension or other. So basically what this does is if the rank is below the rank limit, it's going to return the stack dimension. It's going to return the dimension name. If it's above, it's going to return other. So when that join happens, we'll get all that extra stuff joined into that other category. Now the ranked dimension or other is very similar. The SQL statement is very similar. The only difference there is we're going to prepend the rank number onto the dimension name. And this gives us a sorting capability in the visualization so that we can have the largest value show up first in the pivot. And again, you can see the HTML trick where we get rid of some of the superfluous joins, just like the the other example we gave you. And then we've got a bunch of links. So we're going to have one link for every different possible value that we can stack by. And the link is what gives us that visual drilling capability. When you click on it, you're going to get a list of all those links. And then here's the code behind one of those links. So basically, we're going to re-implement all the filters that are currently set for that dashboard. So when we're drilling, we're getting the same context in that drill through. And then we're going to change the stack by to whatever value was picked on that the pick list. So now we've got all the views. We need to go to the model and make the top-end Explorer. So the first thing we do is we go to the existing Explorer and we hide it. Because we're going to add a new top-end Explorer with the same name. Basically, we give it, the label is the same name as your existing Explorer. So it kind of like gives the impression to the Explorer user that they're actually using the same table. And then we put some default filters in there. And then at the bottom, we have the join that joins this new top-end view with the rank view. And we join on the stack dimension value. That's the basic model for the stack dimension. But now we also were drilling by time. In a large data set, if you've got billions of records of data, you're not going to, and you want to be able to see both very large time frames like year aggregations, and you also want to be able to drill in and see hour level aggregation details. You don't want it to have to aggregate that on the fly. So what we do is we use what we call liquid table steering. So what we do first is we create a base view. And this base view basically defines all of the dimensions that we're going to have in every single one of our aggregated views. So every table that we're going to be steering to is going to have exactly the same set of dimensions, just aggregated at different levels of data, at different levels of time. Then we're going to create those aggregated views. You can use materialized views directly from your connection, or you can just create PDTs and have Looker regenerate those PDTs on a regular basis. The aggregated views are all going to extend the base view. So here's an example for our yellow trip data where we aggregate to the day. So we're going to extend our base, which is just a list of all the dimensions and measures that we have in all of our tables. And then in our derived table, we basically aggregate the data by the time grain that we're looking for. And then we take all those different tables that we created. In this case, we've got a bunch of PDTs, and we modify the original Explorer or original view to utilize the derived table that has a bunch of liquid in it that picks the table that you want based on a time grain parameter that gets set as a filter in your visualization. So let's see how that looks. So here you can see we're changing from hour to day, and you can see the SQL there just updates to week and then to month. So the SQL is automatically updating when you change the parameter that's listed there in the Explorer. So time grain, very similar to the stack by. It's basically a parameter with the suggestions listing all the different time grains that you're going to support in this Explorer. So the time axis is very similar to the other one, where we've got a bunch of liquid statements that look at the time grain parameter and then pick the dimension group value that matches that time grain parameter. And again, you see a bunch of links on the bottom there. That's for the visual drilling aspect of it. And those links look very similar to the stacked dimension links. Again, we have one link for every stackable dimension, and we're going to, in this case, change the time grain to what the selection was on the drop-down. The last thing we need to do is create our dashboard content. So that's pretty easy. We just basically explore our model. We add the time dimension for the x-axis. We use the rank dimension or other as the pivot dimension. We add our desired measure and save it to our dashboard. But we're not quite done yet. We do have to add filters on our dashboard. So now we're going to need a filter for the 4 new parameters that we created, the stack by, the stack limit, the time grain, and the time range. And then we're going to have to add another filter for every single stackable dimension. And then while you're doing that, of course, you have to make sure that you don't make any typos. It's got to match exactly the syntax that's in your links in the LookML. So that can be a little bit challenging. So while this is extremely powerful, there is a boatload of LookML behind it all. So it's really, really tedious to do this for each and every visualization that you have. So basically what we did is developed a Python script that uses the Looker API and automatically scans the Explore hierarchy for dimensions and drill filters, and then outputs LookML for us that we can just pull right into our model. One of the things we do in that to make that easier is we use the tag parameter in Looker. There's a parameter you can add that you can put your own special tag in, and we basically add a tag to any dimension that we want to include in that stack list, and we give it a value of stackable. And so the script's going to go through and it's going to find all those dimensions with that tag, and it throws it into the suggest list for the stack dimension. So, in conclusion, so we've developed a LookML-based visualization to make exploration of very large and complex data sets simple and intuitive. We're basically trying to give people explore capability in a dashboard, but in a very controlled environment. We're using liquid-based table steering to make the performance acceptable for both very long time periods as well as detailed fine time grains. And we're using Python code in the API to generate the views necessary, and we generate in a couple of minutes. And then one single dashboard we have in our EDA environment where we've got 32 different stackable dimensions that people can choose from, 3 base table aggregations that are aggregating by different aspects, and then 6 different time grains, makes a single dashboard able to replace about 600 different dashboard combinations with a single dashboard. It makes it, everybody knows where they go to get their data. It's just this one dashboard. So I'd like to acknowledge a couple of people in the room, Joe, Derek, and Rupa, who helped develop this. And Todd, of course, I mentioned, he's going to help answer questions. And I'd like to thank the Russ, who I see in the back there, who helped us come up with a lot of these tricks. And of course, New York City Taxi and Limousine for all their data that they so graciously put on the internet for us.